Okay, in our previous segment, we introduced the concept of kinetic energy and the concept of potential energy. And now we're going to put the two together to make total energy. So the total mechanical energy of a rocket ship or a planet is going to be the sum of its kinetic energy plus its potential energy. And so there's this thing called conservation of energy, which is very important in physics, which says you cannot create or destroy energy. Now you can change it from one kind to another kind of energy, but you can't just make it out of nothing. The energy had to come from somewhere. So for example, the first picture there shows an amusement park. And in an amusement park, you have a motor that pulls the car up to the very first hill. So you're going to give that car potential energy. So as it's raising the car up to the top of the first hill, and now it's motionless up here before it starts to go down, it has its energy in the form of potential energy, and that energy was given to it by the electric motor that pulled it up. All right, now it's going to start to go down the first hill, and as it goes down, what happens to its potential energy? Okay, it starts to get smaller because there's less height above the ground. Now, you can't get something for nothing. So if you're losing potential energy, it must be turning into something else, which would be kinetic energy. Okay, now kinetic energy is energy of motion. So as it's gaining kinetic energy, what do you think is happening to its speed? It's going to be increasing. Okay, and then when it gets to the bottom of the first hill, it has no longer any height above the ground. So what's its potential energy? 0. So all of that energy must have been converted into kinetic energy. So it's moving very fast at this point. And then what happens? Some of that kinetic energy starts turning back into potential energy as it starts to rise. And now notice it can do that loop-de-loop. The reason why it can do the loop-de-loop is, do you notice that the height of the loop-de-loop part of it is not as high as the original height that it dropped from? Okay, and so that way it's going to have enough kinetic energy to be able to make the loop. So that's an example of conservation of energy. Now the second picture is conservation of energy applied to a planet. So that the planet has, it's going to be located a certain distance away from the star, and so it's going to have both potential energy because of its distance, and it's going to have kinetic energy because it's moving. Okay, now which of the two kinds of energy would it have more of? Okay, it's going to have more kinetic or more potential energy because the distance is larger over here than it would be over here. So a large distance means large potential energy, so that means what happened to the kinetic energy? It would be smaller. Okay, now it orbits over to here, so the R is small, so that means the potential energy is small. So what does the kinetic energy do in order to compensate? It gets large. So it's, in other words, it'll be moving faster over here. More kinetic energy means more speed. But wasn't that exactly what we said when we did it with conservation of momentum? Okay, and we said that the closer it gets to the planet, that it speeds up. Well, this is another verification of that by using conservation of energy. Okay, so here's a sample question. If the speed of a rocket ship triples, what happens to its kinetic energy? Now, don't make a mistake. So don't say, oh, the speed's going to triple, so the kinetic energy is going to triple. No. Look at the formula. The formula for linear kinetic energy is 1/2 mv squared. So you have to take the 3 and square it, so it'd have 9 times the kinetic energy that it had before. Here's some typical energies in joules, if you want to take a look at it. And now let's also talk about power. So P for power, and you notice I make it a cursive P because a regular P it stands for pressure, and we're not ready for that yet. Now, if you just want to use a regular P, that's great with me, but I like to use a cursive P. So power is going to be the rate at which you use energy. So a lot of students think something that is very powerful must have a lot of energy. And in general, that's true. But it's not just the energy that an object has, it's the rate at which it either uses energy or it's the rate at which it generates energy. So it depends on time. So power is equal to the energy that's being used up or the energy that's being generated divided by the amount of time it took it to do it in. And just to give you an idea, the power of our sun is 3.8 times 10 to the 26th watts. Now a watt is a joule per second. So do you notice that power is energy over time? Energy is joules, time is seconds. So a joule per second is the same thing as a watt. So the energy output, or the power of our sun, is 3.8 times 10 to the 26th watts. So that's 3.8 times 10 to the 26 joules of energy is being released by our sun every second. And it's been doing that for the past 4.5 billion years, and it's probably going to continue to do that for the next 4.5 billion years. That's a lot of energy. So here are some typical powers in watts, if you're interested in it. And so we're now finished with this lesson. So if you'll stick around for the next segment, we'll go over the quiz questions for you. Okay, see you then.